till 9, right? You guys,
yeah, what time is it right now?
8:59, so maybe wait just a few more seconds.
Yeah, sure. Okay.
Okay. Whenever you're ready, go ahead and get started.
All right, thank you all for coming out today, and good morning. We are Senior Design Team 10, and the team is comprised of myself, Rob. We also have Tiana, Zari, Ezra. We are working for Dr. Lemay, who is our advisor, and our coordinator is going to be Dr. Thompson. And today, we're really here to tell you about this thermal laser Plantar test, which is this system right here we've designed, and it's a method for examining thermal sensitivity within animals that are being treated for spinal injuries. And this is going to be done by laying an animal on top of our system, measuring their reflexes with a laser. And before we get into like why exactly we're doing this and what we're trying to prove, let's kind of back it up a little bit and talk about what exactly spinal cord injury really means. So you can kind of think of your body as one giant circuit, right? You have sensors, and these could be like muscles, reflexes, neurons, etc., nerves, and they're all going to gather data and send it through the spine to the brain for the brain to do post-processing. So when you have a spinal cord injury, really the brain and the sensors still work. It's just the interaction between the two that's a little bit flawed. So like if you, for example, got hit in the kneecap, typically you'd go, ah, because you'd feel that. However, with the spine being broken, you wouldn't necessarily go, ah, because your brain wouldn't necessarily feel pain. So keep that in mind, because the big question that we're trying to help Dr. Lemay research is if existing spinal cord injury treatments could actually lead to long-term chronic pain. That is a kind of phantom pain. You may have heard that term before within spinal cord injuries. And the treatment in question are these specific proteins. They're called neurotrophins. And they get injected into a patient who has spinal cord injury. And the reason why is because these proteins help promote locomotive recovery. And two proteins in question that he would like to examine are BDNF and NT3. There are other ones, of course. Both of these have similar results in terms of recovery. However, it's hypothesized that BDNF might actually lead to an increase in thermal and mechanical sensitivity, which may be a source of chronic pain. And so you're probably wondering, well, should we stop using BDNF? Well, that's what we're going to try and help them find out. And the way we can do that is actually by conducting an animal reflex test. And what that means is we can get animals that have spinal cord injuries and we can stimulate their reflex, and they're not going to feel it because of the spine being broken. And each of these animals will be given a specific treatment, whether it's BDNF, NT3, or something else. And we can actually, when we stimulate the reflex, see which one will react faster. So like if BDNF promotes a faster reaction than NT3, then it kind of proves the point that BDNF is making these senses more sensitive. And our specific project is really here to create that sort of reflex test apparatus for Dr. Lemay to use, because there are some commercial solutions, which Tiana is going to talk about in the next slide. However, they're a bit flawed.
Okay, so looking at the left of the screen, it shows what a typical Hargreaves test is, which has been the standard for thermal plantar testing since 1988. This is a commercial solution that exists where the experiment is a light bulb that heats up the pole and then records the time. The test itself is about 10K, shown in the figure on the top right of the screen, and this is just the renting price. The Hargreaves is composed of a few key components: a filament to heat up their paw and record a reaction time with a timer, animal enclosure, which is used to test the rat, to allow the rat to get used to the environment for a while, and the controller of voltage. The system is made to be used on rats whose spine is drastically smaller than humans, so rats are not the best representation for humans. The idea being that our project is doing something completely different than this for more realistic results for a bigger mammal.
Okay, so kind of keeping that in mind, yeah, we want to use cats because their spinal length is a bit bigger than, a rat, so it's going to reflect a bit greater in humans. And, kind of breaking down those key components, if we want to design a system where our cats are going to really be comfortable, and creating an enclosure like the Hargreaves test is going to kind of make the cat feel like it's in a cage. So instead, we propose this solution where this is our system we showed in a title slide, and we photoshopped the cat and as visual representation that our cat's going to lay down and be very comfortable on top of this system. And we're just going to stimulate the back paw with thermal laser that is really there as a finite, precise way to stimulate the reflex. And if we kind of imagined exactly what was inside this system, we can start to break down some key components and form a block diagram, So like we said, we're going to need some sort of hardware that's actually going to stimulate the paw and capture withdrawal time. We're going to need mechanical interaction to make that cat feel as comfortable as possible and get accurate results. We're going to need some sort of software to actually turn on and off the hardware and store any sort of withdrawal times. And we're also going to need a user to operate the system. And of course, some of these key components were actually previously purchased by Dr. Lemay before we started working on the system. And he got these components approved by the Institutional Animal Care and Use Committee. So when we took on this project, we said, hey, let's reevaluate these, try to make them work rather than start from scratch.
So here we pull out our key functional requirements. It was important that we had the ability to capture paw withdrawal reflex data. This was really important to stay within the Sustainable Development Guidelines of good health and well-being, also life on land. We are working with animals, so it's important that we abide by the Animal Welfare Act. We don't want any harm to the animal's paw, and we want safe interaction between the animal and our system. It's really important that when we're getting results, we can find repeatability within animal groups. This will prove our accuracy, and we want our results to stay between 10 and 20% range. This is really important for our researchers and their data collection. And it was also really important for a friendly user interface. Future teams may pick up this project, and it's important that they can continue where we left off with no issues. So then moving on to our design constraints. When testing, we needed to stay within a range for test performance per day. So we decided to stay between 3 and 5 trials a day. This abides by the Animal Welfare Act again, and with research of our Hargreaves Test, we saw that they also use this method and stay between this amount of trials. Again, we have a budget. So rental for a Hargreaves Test is about $10K. It was really important that our system was under that and as efficient. And then finally, we'll talk about it later in some future slides, but within our budget, we want the best performance possible in our system. So it was important that we had a functioning laser that would bring us those components.
Our plan for testing is a 3-step process. We broke the system down into 3 components: hardware, software, and mechanical, and are going to develop and test each component first. After we test them, we're going to test the interaction between these components to see how the software interacts with the hardware and the hardware interacts with the mechanical component, and then test the system as a whole before we give it off to Dr. Lemay's lab to test it on the cats.
So expanding upon the block diagram that Ezra just walked us through, our overall system works as follows. The idea is a 5-step process. First, our photodiode gets covered by the cat's paw. The Raspberry Pi reads this as a signal, and then it sends a signal out through the laser driver to turn on the laser. The laser will then shoot up towards the acrylic plate to take an initial timestamp. And once the cat's reflex is activated, it'll remove its paw. The paw removal exposes the photodiode to light, and a final timestamp is taken for that run. In the same instance, the photodiode sends a signal to the Raspberry Pi to turn off the laser. And finally, our Raspberry Pi will calculate the change in time and analyze the results.
Okay, so the following is the proposed solution implementation, which is already described in the previous slide. These are the physical aspects of the system design. You can see that the power supply, the laser driver circuit, and the butterfly connector that she talked about. The switch and laser are connected to the butterfly connector. The switch is important for our system because we want to know when the laser is on and off. The right shows the photodiode, which has the laser mounted on it. Here we have the photodiode signal, which is a resistor bias, and the photodiode signal that will turn on the Raspberry Pi. Okay, there was a laser purchased by Dr. Lemay, but we actually upgraded our laser to a different Q photonics laser. The upgraded laser will be talked about in a few. The laser that's being used, the optical feedback laser 1460-350, which operates by acting like an on and off switch for the diode. The laser was updated because of the current and the effect of the wavelength on the skin. In 2003, there was a study that showed that at the thermal wavelengths of 1400 nanometers, that it shows that it does not heat up the skin, but the wave goes through the skin, stimulates deep neurons beneath the initial skin of the layer, which activates the pain receptors. The laser being used in our solution has a wavelength between 1430 nanometers and 1455 nanometers, which is key for reaching the pain receptors. The output signal itself is wired through a specialized connector, which is great for us because it makes connecting and programming the laser to the Raspberry Pi easy. We first used a laser that had its fiber exposed, and the problem with that is that the beam was too divergent, making the power not be as strong. We changed to a laser that has a connector that will make sure all the power is being exited through the narrow beam. And the next slide will go over more of the foot pad that we're using.
So once you have the laser and the photodiode, you have to figure out, you have to have something as a barrier to not harm the laser or the photodiode using, because of the oils that are in the foot pad or so what we have is we created a acrylic plate, which seen below is version 1, where it's a 1/8 inch depth acrylic plate with a 0.05 inch depth to see if there was any kind of way to stimulate the foot pad without using an acrylic. Once that was reached, we figured out that it could be tested. And then we saw that it wasn't going to be a good enough depth to guide the foot pad over the laser. So then we moved to version 2, where we used a 1/4 inch depth instead of an 1/8 inch depth. That then proved to work. However, the diameter of the groove was not large enough. So we had to go to version 3, where we had to increase the diameter, and that one worked. And then the acrylic plate also allows you to do a more repeatability test, because now you have a set depth between this laser and the acrylic test for every cat that you're going to test. Once you're finished with the acrylic plate, you have to then put it on top of the top plate, and that's where this picture comes in. So after a couple of iterations of using the router as well as SolidWorks to create a drawing of it, we were able to finally get a good iteration where the center of the laser is going to be at the center of the acrylic plate.
Okay, so an important aspect to this project is getting the laser's power high enough to go through the skin layers to activate the pain receptors. The power of the laser is connected to the amount of current that is produced to get the wavelengths transmitted. There are a set of parameters given to us to use when it comes to setting the current's power. We want to measure the current to make sure that we do not go over maximum current. To set the operating current, the following steps were done. First, we had to connect the multimeter to the laser diode current driver. We then placed the acrylic plate that Ezra made over the photodiode that we plan on mounting it over the laser. The next step is to adjust the current by the trim pot, which is a variable resistor, so that we can get a thermal stimulation, which causes the paw to withdraw. We found that it was at 1 amp at 1.7 volts, we could get the thermal stimulation, which causes the paw to withdraw.
Okay, so keeping that in mind, let's talk about the actual software of the system. So I kind of broke the software down into 3 phases for timeline's sake. Phase 1 was all about, okay, can I actually capture and store data? Meaning, can I use Python and the Raspberry Pi to turn on the laser and get signals from the photodiode? And in that stage, we also included a software timeout, meaning when the cat covers the lens and the laser is on, if there's no reaction within 10 seconds, the system's going to spat out an error message and the laser is going to shut off. And this is here to help with the Animal Welfare Act. And 10 seconds was specifically chosen because the Hargreaves test uses 20 seconds as a timeout. But since we're using a finer stimulator, with a laser compared to a light bulb, we decided, hey, we can do this in half. After that was done, I decided to move to phase 2, which is all about creating an actual database. And I used a hash table for efficiency and then focused on exporting all of these results and performing a group analysis to Excel. The third step was then to take this pre-existing structure that I'm going to walk through in a sec and convert it to a GUI for nice user interface. So the system really runs as this. It prompts the user at first, hey, do you even want to begin a test? And if you say yes, then it asks for the cat's name and the group number they're going to be placed in. And then you have a few options. You can either perform an actual trial and turn on the laser and get a reading and store that into the database. And you could keep doing that for the same animal as many times as you want. Or you can test a new animal and you just go through the process again. Or you can finally exit the program, and then that's when all of the database gets stored to Excel. And keeping in mind some of that analysis, Dr. Lemay specifically wanted to see the average standard deviation, and variance for each individual cat's withdrawal times, as well as the groups that they're going to be placed in based on those neurotrophins. And so since we're using Python and exporting to Excel, I decided to look at both of their functions. I kept in mind that these functions are going to be based on population, since we're going to know the exact number of cats and trials that we're going to be performing and groups. And then from that, you know, in both of these algorithms, even though they're slightly different, mu is always going to be the average of the withdrawal times, whether for an individual or a group, and x is always going to be the current trial time that we're looking at. And so keeping these equations in mind for mean, standard deviation, and variance, I went and actually fed in some false data. So this is just data that I made up, and it spat out these. I used them to calculate both algorithms and get an output. So this is the Python's outputs for mean, standard deviation, and variance, and this is Excel's outputs for mean, standard deviation, and variance. And then I decided to take the percent difference, with Python being values for V1 and Excel being values for V2. And we can see that there is little to no percent difference between these two. So that tells us a few things. One, both of these algorithms are spitting out the same output, so we can safely say that our analysis is accurate in terms of actually computing what Dr. Lemay wants. It also tells us, besides testing that software repeatability, that we can actually optimize the system. Since Excel gives us a finer output, meaning that we have more precise measurements, I actually went and used Python to automate Excel to perform all of the group analysis in a post process, rather than do it using the hash table and wasting CPU time on the Raspberry Pi.
So furthering the test of repeatability, our software was validated, but we needed to further test the hardware of our system. We decided to compare results collected by the photodiode to results captured using a GoPro. We borrowed a GoPro Hero 8 set to capture at a resolution of 1080p at 30 frames per second, and an infrared paper sensor Dr. Lemay had to cover the photodiode at an angle and allow the camera to visually capture the laser turning on and off. Since the camera recorded at 30 frames per second, we found the sampling period by taking the inverse, meaning that the camera is really capturing and displaying the same still image every 0.03 seconds before moving on to the next still image. We use this to find where in the footage the laser turns on and off, and extracted the exact frames timestamps. We then calculated the difference using Excel to find the GoPro's withdrawal time. As you can see in the table, we did this for 5 trials. Column 1 is the number of trials. Column 2 is the photodiode times captured by the Raspberry Pi. And column 3 compares the two methods to find the percent difference. You can see at the bottom that we calculate the average percent difference and show those results. So using the same percent difference calculation as before to compare the difference between the GoPro and the photodiode, we found that there was an average percent difference of 1.12%, which validates our target goal to obtain results within a 10% difference. And it's clear how small ours was. Diving further, if we would have had a better camera at a higher frame rate, such as 60 frames per second, we probably could have found differences that were even less.
Okay, so we're going to walk you through what a typical trial looks like for our system. As you can see, we have this sort of screen and keyboard for user friendliness. And the first thing we're going to do is launch that GUI, and it's going to prompt us, hey, do we want to start the test? And we'll enter Zari's name and the group number we're going to put her in. You're also going to really pay attention, since the laser switch is on and armed. Look at this LED, because once we go and hit begin a test right now, you can see the LED is on, meaning the laser is on and Zari reacted. And we're actually going to save that and do it again. So you can see laser's on and Zari reacts. So we keep that trial, and rather than show you another, we could keep conducting trials for different people all day. We want to show you what outputting to Excel looks like. So we're going to overwrite a previous database with my data, Tiana's data, Ezra's data. We tested it all on ourselves. And we're going to show you what opening up that spreadsheet looks like. And when you open it up, you'll see that each group is represented by a sheet. So there'll be a sheet for group 1, and that's going to contain everyone's individual analysis along with the group analysis. Same thing for group 2. And then you will see that the last sheet is actually a sheet that automatically generates a bar graph that's going to show the group average versus the group's standard deviation. And that was per request of Dr. Lemay. And you're going to see what a typical output actually looks like in the next slide when Tiana talks about the animal testing.
Okay, so this slide focuses on the initial animal testing results that were done. We're not able to show video of a cat being tested upon because we could possibly risk violating the AWC. After testing the system on ourselves, we gave it to Dr. Lemay and his assistants who were able to test the cat on 10/04/2022. The cat this was a controlled cat with no neurotrophins because this was done to compile a clean slate for later testing. When looking at the highlighted sections, we can see that the right paw typically reacted within 1.72 seconds, and the left paw reacted within 5.36 seconds. Within the last few weeks, there has been another cat that has been tested, and the results are looking pretty similar. Going back to our goals and our system, the system is provoking a reaction within the 10-second time frame. There is going to need to be a larger sample size to determine any meaningful results and witness how repeatable our system is.
After testing the repeatability and getting Dr. Lemay and his assistant Jose using our system, we asked them for, we created a Google form of 6 questions about user friendliness, which they ranged from each aspect from 1 to 5, with 5 being the most user friendliness and 1 being the least user friendliness. From that, we were given 2 responses, a 97% and a 94% for user friendliness. In addition to that, we also asked them 2 open-ended questions, one regarding with improving the system, in which we were able to resolve by redesigning the lid of the system, and the second question about further work, which will be talked about a little later on.
So here we break down the cost of our final system. We have our list of materials, the individual item costs, the accumulating costs, and who purchased them. We can see that the final design costs about 1.7K, which is approximately 6 times cheaper than the standard Hargreaves Test rental. Remember, that's approximately 10K. And since we took the initial components that Dr. Lemay purchased, we only spent about $182 on the system as a team, with approximately 1.5K spent by Dr. Lemay prior and his lab's funding. And we're very thankful for their funding because we needed these integral parts for our system. Next, we show you a breakdown of our schedule. So we have it broken into 4 parts. We have our senior design paper assignments. We have our hardware component, our software component, and then finally testing. You see in the video that our system is completely up and running. So everything is completed. We just have our final design document to submit December 5th.
Yeah, so kind of recapping, at the end of the day, we gave Dr. May a working portable system that'll allow him to, test on multiple cats and figure out that hypothesis about BDNF and if we should stop using it or not. There's, in terms of future work that's left to be done with the team, like our team, one thing we want to do is actually take our system to poster day and get more feedback on just what people think about it and trying to maybe give another user-friendly survey, because we only have like really 2 outside sources, Dr. Lemay and Jose, who's already seen our system in action. In terms of future work that could go to another team, you can never stop working on this thing. There's always room for improvement. The GUI itself, you could automate that in real time rather than do all the group analysis in Excel and regraph everything in real time. There's plenty of work there. But another thing that came out of the user-friendly survey from Dr. Lemay and Jose is that they are saying, as great as it is to lay the cat down and test them comfortably, it would be also nice if we can have the cat sitting up and test. And we wouldn't have enough time to kind of manufacture something for this, but we kind of propose you can always make an attachment, some kind of clamp with a sling similar to this little happy baby right here. And we can place the cat inside of it and place him over the lens and test as normal. And, with that, we would really like to thank everyone. There's a lot of people here who came out today. We know it's early on a Friday morning. So thank you so much for attending our presentation. We would like to thank Dr. Lemay and Jose for letting us work with him and, do something we've never really done before as electricals and mechanicals. We would really like to thank Dr. Allebeck and Dr. Thompson for overseeing this whole project. And, it was a great experience, but a lot of fun. And with that, once again, thank you. If you have any questions, please feel free to ask. We'd love to talk more.
Thank you so much, team. Does anyone from the audience have questions for them? You can also use the chat. So what questions do you have for the team?
Oh, I see Paul Johnson. Do you have a question?
Oh, no question. I was just saying great job, guys. Y'all
Oh,
did
okay.
great.
I saw the emoji.
Thank you.
I did have one question. When you guys showed the circuit, the schematic,
Mhm.
how does that one detection circuit detect time? That was, yeah, I missed
You're
that
talking
diagram.
about the photodiode?
The hardware photodiode timer circuit, yeah.
Yeah, so basically, this photodiode, we have the actual photodiode right here, and then, you know,
Mhm.
amplifier that's going to go to pin 11 on the Raspberry Pi. And
Okay.
basically, in the software, there's going to be a while loop that's just waiting for a response from this pin. And so when it changes resistance when it's covered, then it goes and takes a timestamp and moves on with the rest of the program. And then when it's detects another reaction, like it'll turn on the laser then in that same while loop, right? And then it'll move on to the next section, right? And we'll wait for another reaction by checking this pin again to see if it changes to what is it, a
Off.
low voltage? Yeah,
Okay, yeah,
exactly.
okay. I
And
got
then
you.
it takes the second timestamp, and then it goes and records the difference.
Okay,
Yeah, I'm
so
checking
pin
the chat.
2 is just pin 2,
Yeah,
that's just 5 volts from the,
That's just to bias to make this an active component.
okay,
To send a signal that the Raspberry Pi could actually read.
okay, I think I see. All right, yeah, I was just curious about that. And then does any other questions from the audience? Looks like we get some stuff in the chat.
Yeah, I'm looking at
Lots
the
of
chat.
good stuff.
Yeah, thank you so much, everyone. We really appreciate it.
Yeah, thank you guys for coming out.
And again, feel free to stop by at poster day. I mean, again, yeah, we're gonna try to bring the system itself. So if you want to see us kind of tase each other with this little laser, it'll be super fun, you know?
The thing is hot.
Doesn't get hot. It doesn't dissipate heat. You can't say that.
Yeah, it stimulates.
Just stimulates it.
The other just question I had was we mentioned about the laser. You had an initial laser that you had that I guess had too
Yeah.
wide of a beam width, didn't produce enough direct energy. What was considered kind of too wide of a beam width or too wide of a energy pulse versus what you were hoping to have?
Yeah, sure. So from my understanding, and I know Tiana could probably talk more about this in a sec, but from my understanding, the original laser that was purchased, like if we imagine the laser coming out of here, the beam itself, because it didn't have this this end connection, it was a different connection, sort of diverged the lens like this. So it kind of spread the wave across the plate, rather than just send one direct sort of beam to the plate. Do you want to talk more about this?
Yeah, so basically, as Rob just said, when we first had it, there wasn't a connector. So basically, there was just the fiber of the laser that was exposed. And so when there was power being released, it would come out like this versus coming out like this with the direct power being released. And so with having that with having the connector, it was more able to have that wire stay in place and then send it out.
Yeah, and another thing too is that another big reason we upgraded this laser is because this one actually had a higher operating current. The previous laser, you could definitely feel it, but you like when we did initial senior design 1 testing, you had to have your finger directly on top of that laser to feel it. Like even moving away from the laser, you didn't actually feel it at all. And like
can you give
when
me a ballpark how much more operating current roughly?
I believe, if I remember correctly, because this one operates, I forget what slide it says. I believe this one, operates.
Oh, there it is. Okay.
I believe the old one was around 800 milliamps.
Okay.
So we have a little bit of a step. And with this too, when we set this, like Tiana explained, we actually did start at this threshold current and just kind of stepped up until we could actually feel something with the lens, you know. And
Right.
like we started to feel stuff probably around, I would say like 900 milliamps and like 950, but it really wasn't until we got to 1 amp that you could feel it. Like beforehand, like you weren't really reacting from it, we
Yeah.
wanted to promote that reaction. So we left
Cool.
it there. And, based on the shut off that we have and the fact that like it's going through a lens and that we really much modeled a lot of our safety features off of the Hargreaves, we think that it would be safe enough for, cat testing.
Cool. Well, thank you very much, team. Really enjoyed it. Thanks for sharing your work. I got to jet to another presentation, but great job. And so I'm going to head out. I don't know if anyone else has any questions, you can talk to the team or you can be free to go. Thanks very much, team.
Thank you all so much. Stop sharing.
Great job, guys. Not enough information on tool pathing, but
I know.
That's for the paper.
okay, cool. Have a good one, guys. Nice job.
Yeah, and thank you, Tony, for oh, he left. Oh, no. Thank you for everything that you helped with us. We couldn't have done it without you. So
You're
And famous Tony, who helped Hezron.
have a good one, guys. Thank you.
Thanks, Tony.